Hello community, so great that you are back. Let's have a look at AGI. Where are we? Now, we have a look at the latest research from Stanford, Harvard, MIT, NVIDIA, and Carnegie Mellon University. So, welcome to my channel, Discover AI, the latest research. Here we have 3 publications, October 1st, October 2nd, October 3rd, and we're gonna have a look. All of those papers have the same topic: improve the reasoning abilities of our vision language model, our large language model. So let's jump into it. We have Carnegie Mellon University and Stanford, and they talk about training LLMs to discover abstractions for solving here the reasoning problems. And you might say, this is interesting. What is it? Second is beyond majority voting. Here we have MIT, Harvard University, University of Chicago, and they go about if you have multiple agents and agents disagree with each other, what about going beyond majority voting? And we're going to have to look at some beautiful formulas. And of course, then we have NVIDIA with Carnegie Mellon University, Boston University, and Stanford University. And finally, we talk about front-loading reasoning. Yes, absolutely. And you know what? All papers disappoint me. And this is me in a different vector representation. If I would be more physically beautiful, why is it disappointing? Let's have a look. First paper. I mean, come on, the conceptual leap is from a monolithic reasoning to hierarchical strategy, and the innovation is that it decouples the strategy from the execution. I mean, come on, this is familiar, no? Okay, now we have an abstraction generator that acts now as a strategist, and then we have a solution generator that acts here as an executor. But this sounds familiar to me, no? And if you argue, yes, it creates now a division of labor for the artificial intelligence, for the AGI, that allows each component to specialize, leading to a much more efficient and effective learning process overall. Yes, we know this. You know what? We reduce complexity. We say it is too complex for a simple AI. Therefore, we have to chunk it up here in several little pieces with reduced complexity because AI is not able to handle complexity anymore. So, just to be sure, this new methodology is not a brand new mathematical algorithm for AGI or AI or anything at all. It is just that they try to improve the reasoning performance. How do you do this? They say, you know what? Let's think about what are the abstractions if we analyze the problems. And we will make those abstractions first-class citizen. And we will optimize those abstractions. We will build a particular vector space, and then we will have a coupled of a proposer and solver agent with a particular learning. Of course, it will be reinforced learning, and of course, it will be something like a PPO, so that compact reusable procedural knowledge emerges and is exploited. And anyone said, okay, but you know, the classical approach for LLM reasoning is either you go with a supervised fine-tuning, you go with a chain of thought, you have a single level reinforcement learning, you have your classical policy gradients on the full solution, and you have an end-to-end with reinforcement learning, or you have ensembling, majority voting, simply re-ranking. We know all of this, and I understand that you just rearrange everything and everybody's looking for a breakthrough. But come on, if you are a subscriber of my channel and you are a brilliant genius, hey, the world is waiting for you because look at those papers. Okay, so let's go back. Abstraction. What are abstractions? Simple, just short natural language lemmas that you make explicit as an AI system and you write it down, you make it learnable, and it is a little knowledge chunk that suddenly is your reduced piece of knowledge, and you build a mathematical space out of this. So instead of relying here on a single LLM or a single agent to spontaneously surface and use lemmas within a long chain of thought or your reasoning trace, the system now explicitly in this beautiful new idea generates short, reusable hints for a very particular query, for a very particular topic, and those hints are now collected and served now here as a basis for solution. So what they achieve now is, if you think about here, you have a solution space, and this is a huge solution space. The moment you start to have here reusable hints, you remember 2 days ago we talked about the concept net and the concept web. This is, if you want the concept, this is now a lemma or a lower dimensional hint space. So reduced from a complex, huge solution space now to a lower dimensional hint space. And you see immediately the limitation we have, that we have to accept. Because if this decomposition of complexity, again, we have here another decomposition of complexity of a complex query that we have now, let's call it, what are they called? Abstractions, lemmas. You know what? What if those abstractions are reducing the complexity? Yes, but are missing out on higher complexity levels, on higher order of reasoning. Because the abstraction that are generated by this particular LLM, this LLM is not capable of going for the fourth order of a complexity structure. Then our lower dimensional hint space is limited. But okay, let's go with this. So we reframe now the reasoning process as a hierarchical procedure learning problem. We make a short natural language abstraction, hint, lemmas, mini procedures, whatever you call them. And we have two agents. We have a proposer and we have a reinforcement learning. We have a policy of the proposer that outputs a candidate. And this is now an abstraction given a particular query. And then we have a solver agent, and then we have a policy, and we have a reinforcement learning that outputs a solution that is conditioned here on the prompt and on the abstraction given. And then we combine here the training, the reinforcement learning here for both. And if you want, the beautiful thing is the proposer is now rewarded with the success only if the solver is successful, and you got the idea. Now, if you look at the system architecture, I thought maybe there's something hidden. No, maybe there's some genius thought about it. Yeah. So we have the proposer with our policy here, with the abstraction, then we have the solver with the policy, with the solver, then we have the reward, and we have the training loop. We have here, we form averages per abstraction, so we are sampling over a bigger set, and then we update both policies of the solver and of the proposer here with a policy gradient that you are familiar. And inference, yeah, you do not know this. This is the third paper, but I already integrated the third paper in the solution for the first paper, but okay. So, what the system learns and why the decoupling helps. They say, okay, our abstraction space is now lower dimensional, and this is correct. We really went from a high complex solution space, high dimensional solution space, to a lower dimensional abstraction space because the elements, the Lego pieces that we build our abstraction space are now our, if you want, little insights. So, okay, is this space complete? I can't tell you. I would doubt it. Okay, we have a better credit assignment, we have a reusable and a transferability. Okay, yes, and we have a controlled exploration. And again, you know, here we again, that we say, okay, we do have a problem if we just go here with the normal reinforcement learning. So what we need to have some entropy, some diversity incentives. And you know, we have a Kuberg library and everything that you're already familiar with. As I told you, we optimize the proposer agent here by downstream utility is trained not to produce a plausible text, but to maximize now the solver success. So we have an interlinked system, an interdependent system. And if you want to see the nabla phi here of our J solver, or the nabla theta of our J abstraction, here you have it, baseline, Kuberg-Glauber penalties, entropy bonus, multi-sampling averaging to reduce the variance and stabilize the learning. Otherwise, we would have collapse. Okay. Here, Kuberg-Glauber, PPO-style clipped, supervised pre-training. Yeah, this is something else. This system is not gonna work. And you say, what? If you do not have a warm start. So this means because suddenly we are here working here in a reduced space, we need here the system cannot start somewhere. But we have to have a supervised pre-training of the proposer of the solver from higher trace summary. So we need to have a higher complexity LLM, a more powerful LLM that gives here a jump start to this one, because otherwise the system would start somewhere and never come here to any extrema and therefore would simply fail. So warm start via supervised pre-training is absolutely necessary. Yes, okay, it is not a monolithic end-to-end reinforcement learning. Okay, beautiful, because we do have this hierarchical decision-making and a hint to a try. Okay, and the policy gradient estimator is the reinforce or reinforce plus, whatever you like. But the limitations are significant. Yeah? So most experiments were done on the mathematical reasoning traces, and the transfer to any open-ended task is simply left open. So great if we have verifiable mathematical problems, but what about open-ended task? Is the system going to work at all? Unknown. As I told you, the abstraction generator must be warm started here by a stronger LLM or vision language model to bootstrap at all, that we have an ignition here of the engine and training a single model to both the proposer and the abstraction via reinforcement learning. You have immediately a training collapse. So you need different models. Why? I can't tell you, but it's not working. Beautiful. Now we have here the second paper now from NVIDIA, Carnegie Mellon University, Boston University, and Stanford University. And here you find it. Unfortunately, I could not find here the publication by NVIDIA on the Archive server. Yes, of course, it's proprietary. What are they telling us? They say, you know what? We still have a problem. We don't know when should we train the system for reasoning. Should we have a front-loading reasoning? This means should we do this in the pre-training phase? Or should we go with the reasoning, the main reasoning effort, and should we invest in the post-training data phase? What to do? And the solution is easy. It only works in the pre-training. Great. Let's have a look at this. They did a huge experiment, measure when pre-training versus supervised fine-tuning and what type, diversity, quality, and scale of reasoning data should be injected, under what data, to what amount, how to optimize here the reasoning after reinforcement learning. Front-loading matters. This is the result if you want. Injecting the reasoning data during the pre-training gives you here the highest gains that even if you have then a supervised fine-tuning and reinforcement learning, the supervised fine-tuning alone cannot fully recover. You have about plus 20% better. So therefore, you have to import or already have the pre-training complexity of your pre-training data that you have to do in the pre-training. Otherwise, you cannot have this simply inject in the supervised fine-tuning phase. You have an asymmetric allocation principle. Yes, of course. High-quality pre-training can also be hiding. So you maybe see just a small immediate effect if you only go with the pre-trained model. But the moment you do a little bit of a supervised fine-tuning in the domain of the pre-training, in the complexity level of the pre-training, suddenly you unlock all the gains here and your supervised fine-tuning performance will make a big jump forward, upwards. Great. So high-quality pre-training can be latent. And if you think you just invest in supervised fine-tuning and you flood the supervised fine-tuning with mixed quality examples, NVIDIA showed us and they did all the experiment. Please have a look and read the paper yourself. Mixed quality examples degrade the performance and supervised fine-tuning, nothing. You lose performance. Great. So what are the recommendations by NVIDIA? How should you, according to end of September 2025, do the pre-training supervised fine-tuning and reinforcement learning if you want to improve the reasoning traces? Put diverse reasoning patterns with diverse complexity, with diverse length into your pre-training dataset to build flexible foundations. Then, if you have done this and you have the seeds already in the pre-training model, then you go use a small, really small, curated, high-quality supervised fine-tuning traces to align, to activate here the capacity and activate here the latent capabilities. And careful if you evaluate anything, don't go for independent stage evaluation. You have to evaluate here in the complete complexity of the system. And then we have the third study, MIT, Harvard, and Chicago. Now what they say we have a problem. We have a problem. We have multi-agent system, no, and the agents have different LLMs here as the core, the reasoning core. Maybe we have an LLM2, maybe we have an LLM3. Maybe the LLM3 is a variant of the LLM2, but maybe we also have other agents here from a vision language model 1 that is completely different, has a different training set and is a different supervised fine-tuning, a different reinforcement learning from LLM 1 or 2 or 3, and LLM 1 is also completely different to the VLM 1. They don't have an interlink, and when they should cooperate and when they should come to a conclusion, they completely disagree. So who wins the augmentation? The one who is shoutest, the strongest, the most beautiful agent, the smallest agent? So they say, what happens? And they say what we have currently is a majority voting system. This is a zero-order methodology, and it only uses here the raw answer 1 to answer n, that treats every agent, every model equally. This means it ignores two critical pieces of information, two dimensions of information. First, the first order information. This means the individual accuracy of each model. If we have a model that has an AGI coefficient from 0.4 and we have a model that has an AGI coefficient from 0.01, both models are not equally. Don't treat them equally. Second order information, the correlation between different models, between different agents. If you have 4, 5, 6, 7 agents, you can now work with this because now you have multi-correlations that you can calculate and find out who is the best in the bunch. Let's have a look at this. Why are second order signals so important? Why those are now the hot topic? It is the information about multiple pairs of agents and how their answers co-occur. And as I told you, models can be correlated. Maybe they have the same training data. Maybe they have the same transformer architecture. Maybe they have the same heuristic bias. Maybe they have the same whatever. You don't know. If you have multiple LLMs in your agents, you have no idea it's a black box. So therefore, you have to test it out. You have to do trial and error, and trial and error, and trial and error. And then you get information about a second order signal. So two orders agreeing does not necessarily double here the evidence if they usually error together. Now, pairwise statistics, on the other hand, allow us to detect here the effect of herding or group thinking among the agents, among the LLMs, among the VLMs or cross VLMs, ALMs, and the downward redundant agreement. But you know what? Even a minority answer, if you have 7 agents and 6 agree and 1 does not, this minority answer can be more credible if the minority model tends to disagree with the majority in ways but that indicate correctness. So, this is now an interesting paper. Finally, a little bit something of a challenge here. So, if we're using second order signals here, we say, hey, given that we have a model B and a C, or an agent B and an agent C, and we have now a result X, how surprising is it, probability surprising, that now the model A says Y? Now you have to test this out. This is across correlations and whatever. No? You want now to know how surprised are we, statistically surprised, mathematically surprised are we, to update which answer is most likely correct. So you have to do a lot of testing. Now, but let's start here with the first order information. And they call this here, NVIDIA calls this the optimal weight. So here we go. So when the model accuracies are known, when you know the performance of your model, this model assigns now an optimal nonlinear weight to each of the model vote. You have simply weighted here this, and it's a simple formula. Everything is great. If you want to have an example, I asked GPT-5 here to just come and build me an example. So 3 models with the accuracy A, B, C, then we have the weight, just the log. Suppose the question is true, false, false. Then you have the score for the true, the sum of the weights of the model voting true. This is here, in our case, only WA. So this is the score for the false is WB and WC. And this is here, and you see here, since 1 is here greater than, the weighted vote picks here true. Correct given a strong first order reliability. While the simple majority would pick false. So you see, nice. Okay, but you know what? Even better, a second order information. But careful, you have to invest quite a lot of time and money and infrastructure. So, which model tends to agree? Which models disagree systematically with the crowd in ways that historically correlate of being correct, or which answers are surprisingly popular given the model's pairwise tendencies? Let's have a look at this. Now, you know the surprising popularity, and guess what? Here we have, because we're working with LLMs, the inverse surprising popularity. Computer second order statistics here, you're familiar empirically, and score each candidate by the gap between the observed popularity and a counterfactual predicted popularity. This means averaging prediction when other agents' answers were different. An adaptation of the surprising popularity and inverted for the LLMs improved over majority voting. Now, as I told you, this, if you have not the data, this requires here many model calls. but it is typically still cheaper than you would hire 100 PhD students for the human labeling of the data. So you see, we say, okay, I pay more for the compute investment because the 100 PhD or your expert, human expert, would be even more expensive. So you use, careful, statistical higher order signals, accuracy correlations to improve here your ensemble decisions, your 7 agents, your 12 agents, whatever you have. But remember, the more agents you have that communicate, the more errors you have in the communication channels itself. When does this new ISP outperform here the majority or the naive voting? If the model accuracies are completely unknown or unreliable. If the models are absolutely heterogeneous and correlated, some models share the biases they have, others provide independent information, and the correct answer is held only by a minority that historically disagrees with the majority in informative ways. Maybe the minority is here a professor of theoretical physics, no? And the historical majority are the students in the class, you know? You get the idea? Great. So, second order methods exploit who disagrees with whom and when. And this is all the information that a majority voting just simply throws away. So you see, we just want to figure out who is right if you have 7 agents. But careful, you have to invest a lot of time and money here for second order information of the complete system, given here a very narrow domain, given here a very narrow complexity channel, given here a very narrow manifold. Okay, as you noticed, we have in all 3 papers an asymmetry of information and an asymmetry of compute. And it's quite a striking pattern, yeah? Because the first paper here, the compute asymmetry, yeah? An asymmetry value in allocating test time compute. And again, in reinforcement learning, we always have here this very sensitive equilibrium between exploration and exploitation. And here, this is absolutely the same. Front loading here, the reasoning, no? We do have a data asymmetry. And what I just showed you beyond here, the majority voting, we have an information asymmetry. There's an asymmetric value in the information orders. Yeah? The 0 order information, the vote here, is weakly predictive. The first order, the accuracy, and the second order, the correlations of multiples information are dramatically more valuable for a robust aggregation, but you have to invest time, money, and infrastructure. So there you have it, 3 brand new papers, all selected only for you, my subscriber. And if you ask, hey, where are we today with AGI? Don't make me cry. Subscribe, and I see you in the next video.